Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is position time graphs. So for the first time in this unit we're going to be looking at a way of using graphs to predict and to describe motion that's going on. So far we've just been using equations. Take a moment to pause the video and look at some of the questions we're going to be answering, as well as where we are in the unit schedule, and as well the learning goals and success criteria. So do that now, please. Okay, you're back, and we're going to get started right off the bat. I'm going to ask you to take a look at this graph. This actually comes from your textbook, the book being Physics 11 by Addison Wesley, and it's probably one of the more simple position time graphs that you're going to see. Let's talk about what exactly a position time graph is, what information we can get directly off the graph, and then some other calculations we can do to get some sort of hidden information out of the graph. So first of all, note that this axis, the y-axis, is plotting the position, that would be the symbol D, of an object that's moving, and the position is measured in reference to someone's home going in the eastward direction. On this axis, the x-axis, we have the time measured in hours. So first observations, if I look at what's going on, it seems that the object begins at a time of 0 at a position of 0, which would put it right at the home. In the next hour, it makes its way all the way up to what the book has labeled point B, which is 80 kilometers east of home. So the object is obviously moving to the east. Something to notice, the rate at which it moves is very steady. Because this line is straight, that means that every time the object goes, let's say, 20 kilometers east, it takes a certain amount of time. And then another 20 kilometers east, and the same amount of time. And then 60, and so on. So this is describing constant velocity, and that's one of our first observations that is sort of the hidden information on a position time graph. A straight line represents constant velocity. Okay? As we continue moving, we're continuing to go east of home, only this time the slope of the line has changed. Now something to notice here, in the first part, A to B, if you take a look at that slope, slope of course is rise over run, and another way of thinking of slope is y2 minus y1 over x2 minus x1. All of the math ideas from grade 10 and 9 still apply. The slope, which is rise over run, that's a rise of 80 divided by 1 hour, 80 over 1 for a slope of 80. For B to C, I'll let you do the math, but the slope comes out to be less than 80. In fact, it looks like going from 80 up to 150, so that's a rise of 70, only this time the run is 2 hours, that's 35. So yes, there is indeed a lesser slope in B to C than there is in A to B. But what does that mean? Well, it means you've traveled less distance in the same amount of time, or less displacement in the same amount of time. What these slopes are actually measuring is the velocity. These are velocities. They are rises, which are measured in kilometers, divided by runs, which are measured in hours, and therefore their units, which are hard to squeeze in here, but I'll do my best, kilometers per hour. Same with this. And they are also in a certain direction, which would be east. Can't see that very well, so let me just move that over. Kilometers per hour to the east. So not only does a straight line represent constant velocity, but the slope tells you what that velocity is. So that's a major observation that's not apparent right off the bat. You have to sort of dive into the graph and make some calculations before you notice that. So not only can we read positions directly off it, we can calculate the velocity using slope ideas. Here's an interesting one. What happens in the interval C to D? In the interval from C to D, you'll notice that the slope is 0. It's a horizontal line, and you know from grade 9 or 10, slope is 0. in a horizontal line. And therefore, that would mean that the velocity is 0. Is that the case? Well, let's look at the position once again. The position is about, let's say, 150 kilometers east of home. And yeah, sure enough, as the time goes by, the position is not changing. So it really does seem to be true. Slope is velocity on this kind of graph. And as I mentioned before, a straight line represents a constant velocity. Now, let's look briefly at what happens from D to E, because this one now has a slope that's going down. So D to E, in math class you learned that a downward slope is a negative slope. And if we do rise over run, we will now have a negative number. In fact, we started off at 150, we went down to 60. That's a rise of negative 90. The run is from 7 to 9, that's 2. So we have a negative 45 slope, which means negative 45 kilometers per hour in, once again, the east direction. What do we mean by this as our velocity? We mean negative east in the same way that we mean positive west. Now, how can I convince you that this is the case? Well, I think I can do it if I get you to believe that here you were going away from home to the east, and here you were coming back home, so you must have been going west. All right? So keep your eyes open for negative slopes as well when you're making these calculations. That's going to mean you reverse the direction of motion. Okay? One last thing for a position time graph. We've been talking about velocity, but we've left out velocity's cousin, speed. If you recall, speed comes from distance, whereas velocity comes from displacement. Since displacement and distance are different, therefore velocity and speed are different. What would be the total distance traveled in here? Let's take a look. You go 80 kilometers to the east. You go another 70 kilometers. You've gone 150 kilometers in both distance and displacement as you move away from home. However, here you stopped, and then on the way back, you return over that same distance. So now your delta D is negative 150. You have returned home. But remember, distance keeps adding up. There's no such thing as negative distance. So actually here, we just tack on to the distance that we had here. And in the end, the total distance, we just add up everything. We add up the total path length to give us 300 kilometers, 150 plus 150. Of course, the total time for the trip is 12 hours. And from this, you can calculate the average speed, which of course 300 over 12 going to give us 25 kilometers per hour. But what would have been the average velocity? Can you see what it would be? You started off at 0 kilometers east of home, and you went away from home, stopped, returned home. Since you returned home, your total displacement was 0. And so remember that fact of the day from the previous video. If your total displacement is 0, then your average velocity is also 0. So there's a comparison of those two calculations on this graph. Moving along, let's take a look at a slightly more complicated graph. This graph has curves on it, and what does it mean if the graph that we're dealing with is curved? Well, just like here, the straight lines meant constant velocity, the curved lines are going to mean the velocity isn't constant, which means the velocity is changing. So one of the rules, curves mean velocity changes. Now, if the velocity changes, does it make any sense for me to ask you what is the velocity? The answer is no, because the velocity keeps changing. There is no one single velocity. I could ask you what the average velocity is. If I asked you for the average velocity, you would look at your definition for average velocity. It's the change, the delta in position, delta in d, divided by time. And so for this object, which is described by a position graph showing the position of an object going down a ramp from a start, the object progresses down the ramp, 0.2 meters down the ramp, 0.4 meters down the ramp, 0.6, and so on, and then it's less than that many meters down the ramp, it's going back up the ramp. So if I were to ask you for the average velocity, I would have to say over what time interval? Over the total time interval, the average velocity once again is 0. The ball gets back, or the object gets back to where it started. But suppose I asked you for the average velocity from time 0 seconds until time, what's that time there in the middle? 0.8 seconds. Now you would need the displacement, the change in position. Well, we started at a position d equals 0 meters down the ramp from the start. And after 0.8 meters, after 0.8 seconds of time, if we take this to be the end over here and this to be the start, then at the end the position was, looks like about 1.3 meters down from start. So what would be our displacement? That's easy. From 0 to 1.3 would be 1.3 meters down from the start. And of course the time, which would be, sorry, I believe I said 0.8 here. The displacement would be 1.3 meters down from start. The time would be 0.8 meters, sorry, 0.8 seconds. And therefore, you can do a calculation here. Just run this through my calculator really quickly. We got 1.3 divided by 0.8, giving me 1.6 to two significant figures. Meters per second down the ramp. Now, you see what I just did here, even though I didn't show you on the graph, was I just did a rise over run calculation. In fact, if you imagine that these 2 points are connected, then really what I did is calculate the slope of this line. Even though the graph didn't actually follow that line, this is kind of like an averaging line which kind of takes into account the overall average motion between these 2 times. And we have a name for that kind of line that connects 2 points on the graph. It's called a secant line. A secant line is used on a curved position graph to get you the average velocity. So remember that. In fact, this is one of the facts of the day for this video. So if you're getting ready for that little quiz that we have after these videos, this is one of the facts of the day, that on a curved graph, the secant line joining 2 points gives you an average velocity if you calculate its slope. But we still haven't answered the question, what about instantaneous velocity? How do I get v instantaneous on a graph? Well, first of all, you have to specify at what instant do you want to know the velocity. So suppose on this graph I wanted to know the velocity at, I don't know, let's say at this time right here. Suppose someone asked me, how fast was this object moving down the ramp at time 0.6 seconds? Well, how do you calculate the slope of a curved line? Here's where you got to borrow an idea from math class, which I think you've learned. I hope you've learned it. You have to draw what's called a tangent line. What does a tangent line look like? Well, to tell you what a tangent line looks like, I'm first going to ask you to imagine a circle. A circle has curves, so we can talk about this thing called a tangent line. A tangent line is a line that just barely touches a curved surface at a point, and that point is called the tangent point. And the line is called the tangent line. Now, what does a tangent line do to help us find velocity here? Well, look at this. If I zoom in, and I'm going to zoom in a lot here, I just want to quickly make the point to you that when you zoom in a lot to a curve, take a look at this. The tangent line and the curve are kind of the same just near the tangent point. They kind of take on the exact same slant or curve or slope. And therefore, a tangent line to a certain point on a curve gives you a good idea of the slope at that point. So what we're going to do, after I finish unzooming here, is we're going to draw what's called a tangent line to the point in question. Now it's not easy, I'm warning you, for me to draw tangent lines in Sketchbook Express. This tangent line, unfortunately, is not very good. It hits the graph right over here. I missed. I'm going to try maybe one or two more times before I give up. There we go. Got it. This line here touches the tangent point pretty closely, good enough for the purpose of this video, so that I can say, hey, one point on the tangent line is this point here. Its coordinates are x comma y, 0.60 comma y, I don't know, maybe 0.70. And another point on this line, here's a good one, this is easy to read. This point is 1.00, comma 1.40. So if you want the instantaneous velocity at this time, that's still a slope, but it's not the slope of the curved graph because there's no such thing as a single slope to the curved graph. There's many slopes. So we sort of pick out the slope we want by calculating the slope of this tangent line. Slope of tangent line. And that's going to be a y2 minus y1 over x2 minus x1, just like it was in math class. Or if you prefer, rise over run. They're the same thing. What do we get here? My y2 value is 1.40. My y1 value is 0.70. My x2 value is 1.00. And my x2 value is 0.60. That gives me 0.7 over 0.4. What are the units? Again, the rises, the y values are in meters going down. And the x values are in seconds. And if you punch this into your calculator, 0.7 over 0.4, that's like 7 over 4, which is 1 3/4. 1.75 meters per second going down the ramp. That's how fast this object was moving at this instant. Of course, it was moving slower beforehand and faster at a later time. However, the instantaneous velocity is the slope of the tangent line. And that, my friends, is, along with the secant line idea, the fact of the video. That if you're on a position time graph that has a curve, you can get the average velocity using a secant line. You can get the instantaneous velocity using a tangent line. Just calculate their slopes. Okay? Moving along. Here's a graph that I've created for you. You can take a screenshot of this, or you can just pause your video and work this on your own. But what I'd like you to do, and you can take this up in class with me if you like, is look at what's going on. It's the position time graph of a student who's chasing a dog who's eating her homework. That's a terrible thing to happen. The dog ate your homework. Good excuse, by the way. The position of the student in meters west of her home is given as a function of time in seconds. And you can see there's a straight line, constant velocity, going what direction? Going west, away from home. Now, a horizontal line, a zero slope. Oh right, zero velocity, we learned that. Student stops and maybe tries to get the homework out of the dog's mouth. Now there's movement again, but it's curved on this graph. So part C has a curve, and what would that mean? What are you doing when you're curving this way? Well, you're changing your velocity for sure, but is it speeding up or slowing down? I wonder. Look at those tangent slopes as a hint. And then in part D, now you're curving your graph this way. Is that speeding up or slowing down? Look at your tangent slopes. Now you're stopped again. Now you're returning home at a constant rate, and so on and so on. What I'd like you to do is analyze this graph and record the analysis the way I just did in words. Record them on a separate sheet of paper like this. Write down your observations in words for each of the lettered intervals. But there's more to it. This graph drops below the x-axis. What does that mean when you go below the x-axis? So also think about that when you get into the later stages of this analysis. Use words first, but then use mathematics. Calculate slopes of straight lines and write those down in here as the velocities. Furthermore, when you see curved intervals like C, D, G, and I, there's no way you can talk about the velocity because there's changing velocities, there's many velocities, there's no single velocity. So you might want to practice drawing your tangent lines and calculating your slopes to get an instantaneous velocity at a given instant. For example, maybe just to check that you're doing things correctly, pick a point in here, let's say right along there at a time of 52 or 3 seconds. Draw a tangent line as best you can and calculate its slope. Find its instantaneous velocity and record that perhaps on here. All of your observations in words and in calculations, you can bring that to class and discuss with your neighbors, or you can bring it to me and we'll have a look to make sure you understand this stuff. Finally, I leave you with an invitation to play around with this physics of motion and graphs by going to a website called PhET. And if you type in PhET, it's from the University of Colorado, a series of scientific and mathematical simulations online and free. You can download them to your computer. And the one that we're going to look at is called the Moving Man Simulation. So in a moment, we're going to go and check that out. Here's what I'd like you to do. When we play with the simulation, I want you to imagine a story about motion. What kind of story? The same kind of story that this graph over here was trying to tell you about a girl who's chasing her dog who's eaten her homework. She moves away from home at a constant velocity and she stops. And then she changes her velocity in this way, which I'm not going to tell you because you've got to think about that. And then she stops again. And now she moves back toward home and so on. Make up a story, any story at all. Then go to this website and there's going to be a simulation where you can actually act it out using the simulation and watch the graph get produced while you move an object according to your story. Let me show you what I mean. So here's what you're going to download. It's going to be a simulation looking like this. It's got, as the name suggests, a moving man and a position graph. And watch what you can do. You can drag the man around and drag him slowly. You can speed up. You can slow down again. You can stop. You can move and stop again. All the while, a position and time graph is being produced. When you're done, you can pause the graph and you can play it back to see what was happening. Or you can say, nope, I don't like what I did, pause it and clear it. And start again. So what you're going to do once again, go to PhET, P-H-E-T, go under Simulations and click on Motion. When you click on Motion under Physics, you're going to get to the Moving Man. Click either Run Now or Download. It's going to make you download either way. It is safe to download this. It's a Java program, very simple, and then you can run it. And this is what's going to pop up. Now I just have to warn you, the first time you run it, you're going to see velocity and acceleration, two other kinds of graphs that we haven't done yet. Just X those out and get to this. And remember, make up a story about the man moving and then act it out. You could say something like, suppose the man begins at a position of -4 meters from the start. Type that in and they will move the man there. Now once you start moving them, the time starts going. So you might want to use your mouse pad to click and drag. You might say something like, he slowly walks all the way toward the origin at a steady rate until he gets to the origin, and then he stops. Now you see what's happening. Now he goes slowly and then speeds up and goes really fast and then stops suddenly. Now he quickly goes back to where he started and gradually slows down and stops. Whatever you choose to do is up to you. It's important that you play around with this and then make up a story and try to act it out. It's tough to do it at first with the mouse pad, but you'll get used to it. And then, once you're familiar with that, make up a story and predict the position time graph, and then act it out and see if you get that same shape. If you get roughly the same shape, great, you understand position time graphs. If you can't quite reproduce what you predicted, it means you need more practice. And that is, of course, what we'll be doing in class. All right, thanks for watching, and I'll see you later.